A very good afternoon, ladies and gentlemen. My name is Peter. I have been with Cisco since 2016, and even before, I loved to dig into routing protocols that Cisco made. And somehow, I was very keen about all those that looked like black box protocols and black box mechanisms. EIGRP used to be one of them. And somehow, even before I joined Cisco and I worked at a university in Slovakia, EIGRP became my interest because there was so much hype about it, so much fame, so much claims that seemed to be almost too good to be true. And when I landed in Cisco, I happened to help with the RFC 7868, which is the open documentation about the basic EIGRP specification. And knowing about how EIGRP works, I would like now to share some of these details with you. This is not really about anything that goes to certifications, although if you know these things, you will probably know more than the folks writing the certification exams. This is simply about you knowing truly what goes on under the hood of EIGRP. And by the way, if you hear that EIGRP is dead, that's not true, because let's face it, there's no better distance vector routing protocol than EIGRP. Now, the better link state protocol is ISIS, right? I die on this hill. ISIS is the best when it comes to the routing protocols. So without big ado, let me go to the first hype that you see so often described in textbooks, in courses, or even simply in the information out there. And it says, EIGRP is a hybrid combining the best properties and qualities of link state and distance vector routing. Please hands up who has ever seen or heard this claim. Okay, probably everybody. Is it true or is it a myth? Okay, so hands up who thinks this is true. Hands up who thinks this is a myth. Well, it's more people. Okay. A protocol is either a link state or a distance vector or a combination of both based on what information it builds the routing table on. Link state protocols create a map of the whole network. Every single router in an area knows precisely how many other routers are there and how are the links stretching between the individual routers. That's link state. Distance vector means I get a list of known networks from my immediate neighbors, and the list of networks includes the information on this is the address and this is the distance. Done. And that's the vector in it. Now, let's look at a true link state protocol and what it would do. I'm running a small topology on my laptop, and I'm not going to tell you upfront how it looks like. We are going to discover it. And I'm going to use ISIS to help you discover it so that you can see how the link state protocol does things, so that we can see how EIGRP does things differently. I'll be jumping back and forth between the slide deck and a topology running in my Linux machine, so please don't get too confused about that. So, I will make the letters a little more visible, hopefully. So, I have a topology running here, and I am in fact running both ISIS and EIGRP here just to show how the two behave differently on the same network. Now, as I said, if I have a link state protocol and ISIS as such, it will create a complete map, and every single router will know the complete map. So I won't be jumping over multiple routers. I will be pulling out the information from a single one and drawing the topology picture by picture. So now, please don't get at all confused about all the columns here. And I see I will need to move the window a little to the right so that you can see better. And maybe make it a little smaller too, because now it's a little out of shape. Here we are. Only focus on the first column. That's the list of the routers. All the routers in this area. Hey, there are 5 routers. They're called R1 through R5. How convenient. So if I were now to draw a diagram, I can immediately put 5 icons of routers in the diagram and say, hey, I know that there are 5 routers here. I don't know yet how they're connected together, but I already know there are 5 together, seen from a single router. These are not necessarily my neighbors, and they are not. And now for the topology, I will start digging deeper into the working database of ISIs. And again, this is not an ISIs session, but I'm showing what a link state does. So I will ask the router and say, hey, detail include IS. Tell me how the router R1 is connected to its neighborship or neighborhood. And I get an information, the router R1 is connected to 3 neighboring routers, R2, R3, and R4, and some metrics. I can go on now and ask about the next router. How is router 2 connected to its neighborhood? Well, router 2 is connected back to router 1 and to router 5. I can ask about router 3. Notice I'm not moving between routers. I'm operating a single console here. I'm working on R1, but I am pulling the detailed puzzle information from the link states. R3 is connected again to R1 and R5. What about R4? You're starting to get probably the system here. R4 is also connected to R1 and R5. And if I asked about R5 now, we probably guessed it connects back to 2, 3, and 4. 2, 3, and 4, just not in the same order, but who cares? So if I now took this information collected from a single router, a single working database, but detailed information about every single router, every single link between a pair of them, and drew or started drawing a topology based on this, I would be ending up with something like this. 5 routers. These were the links from R1, including the costs. This was the link from R2. Well, one goes back to R1. I didn't duplicate one. And to R5, one link from R3 to R5. Finally, one link from R4 to R5. And this is my complete topology, including the costs of the links. And notice that somehow nobody talks about addresses, because link state routing protocols focus more on topology rather than addresses. Addresses are more like a side effect of all that thing. Of course, we care about the addresses in the end. So I can ask, let's say, what network or what IP prefix, what network is directly connected to some of these routers. And so that I don't jump back and forth too much, this is how I would ask on R1. Hey, please tell me what is the network directly connected to R5. Now you see I'm using the modern IP protocol here, not the legacy one, right? This is IPv6. And I'm getting the information that R5 as a router connects directly to a network 2001 DB8 : 5/128. So if I put this in a diagram too, I end up with this topology. And I could be asking about directly connected networks also on other routers and slowly put it all into the puzzle. And once again, from a single router that knows about everybody else in the same area, draw the complete topology of the network. That's what I could do with a link state. And this is how the network in my topology looks like. Now, link state protocols have a link state database. What is the name, if anybody remembers, what is the name of a similar working database in EIGRP where we do the computations? Anyone? Topology table, precisely. Now, the topology table is a little lofty name for what we have here, because we see topology here, but let's see if there is a topology inside the EIGRP topology table. Jumping back to EIGRP topology. Voila. This would be the topology table for this network. If somebody is shocked that there are too few networks, this is because intentionally I'm running IPv6 EIGRP here so that I don't need to assign addresses on the links between routers, just to the end networks. This makes my output for you cleaner. And also, since I'll be doing a debug or two, this will make the debugs cleaner, just for the sake of clarity. Okay, what I get to learn here is that there is that destination network, but I don't exactly know where it is. I just know that there are two neighbors who tell me something about it, that they are somehow far from it, and there are those distances. We'll be talking about them in a little. But I do not know how many routers are here. I do not know how the links run between those routers. I don't know the costs of these links. Nothing of that sort is hidden here. What I have is essentially network distance. Network distance. And no matter how you call it, this is a distance vector. Now, when EIGRP first came about, it was roughly 1993, 1995. It borrowed some ideas from link state protocols that related mostly to establishing relationships, having adjacencies, using hello mechanism, being event-based rather than timer-based as RIP is, but that doesn't make it a link state. That just helps you to do things efficiently. So it might have been a good marketing term then to call EIGRP a hybrid, but honestly, it's not. It's a full-blooded, advanced distance vector. So that's myth number one. Let's go further. And I'll be asking you people a little more questions, and this is just what we have just seen. Oh, this is my favorite pet peeve. Feasible distance. They say it's the best distance to the destination, or the best metric, or the best lowest cost to the metric. Who thinks this is right? Once again, feasible distance is the best distance to the destination. Who thinks this is right? And who think this is wrong? A few people? Okay. Gentlemen, don't spoil the fun, please. So, before I can talk about what feasible distance truly is, I have to bore you a little with the terminology. Just a reminder of some of the arcane vocabulary that EIGRP is using. And to be honest, Cisco is not the fault here. The terminology was taken by a paper from a professor at the time who developed and mathematically proved the algorithm behind EIGRP to be loop-free. Dr. Garcia from SRI International. And he used the terms as passive, active, feasible, and so on. So we just took it. So, as a quick refresher, when I talk about a route in the EIGRP that is in passive state, people sometimes think that it's a bad thing because the route is passive as if it was not working. But in reality, a route in passive state is a good usable one because EIGRP is happy about it. It doesn't need to search for a new route toward it. Essentially, a route that is in passive state means that I, as a router, can make my choices locally and completely safely with what I know. If I need to choose another next hop, I can do it, and I have enough information to make a choice that is guaranteed to be loop-free. Guaranteed to be loop-free. That's a unique thing. That's passive state. If I am in an active state, well, the local information I have is not enough for me to make a 100% guaranteed choice. In that case, I need to ask and coordinate with my neighbors. And my neighbors may in turn need to coordinate with their own neighbors. That's what's called the diffusing computation. And I'm coordinating simply because I want to avoid any routing loop, even a transient one, just a temporary one. So the whole thing here is about EIGRP never ever causing a routing loop. Even if the network changes wildly, and even for a short period of time, no, in EIGRP, that never happens. If it does, it's a bug, right? If it ever happens, that's a bug. You need to report it. Now, and this is what I'm going to ask you. What is what EIGRP calls reported distance? What is a reported distance? Sir? The suggestion was that the reported distance is the feasible distance of my neighbor. We're close, but not precisely right. But we're getting there. It's a good one. Neon says it's the distance that the neighbor advertises. And essentially, yeah, the simplest answer here is the correct one. Reported distance is the distance to a destination as my neighbor told it to me. It's his momentary distance that I've learned from him. As simple as that. What is the computed distance? You may not have found this in older textbooks, but we call it like this now. Well, not to tease you too much. That's the total distance through a given neighbor if I also take the metric of the link between me and the neighbor into account. So essentially, it's his reported distance plus the cost of the link between me and him. That's all. And if we do this output from show IP or IPv6 EIGRP topology, these are the distances when highlighted in colors. We always first see the distance with a given neighbor. We see a distance through neighbor, the total one, and then his own reported one. So the first number will always be higher than the second one because the first number includes the link of the cost of the link between myself and the neighbor. Always. Now, let's come to the feasible distance. So, what do you believe is the feasible distance? Or what do you remember being said about a feasible distance? There is a suggestion that it's the distance through the feasible successor or feasible next hop. It might, all right, getting there, you might be surprised. Very formally, and if you want to read it, do it at your convenience, but let me put it simply. It is the record of how close you were to the destination in the past. It's not your momentary distance. It's essentially the closest you have ever been, the measure of how close you used to be to the destination. It may be equal to your momentary best distance, yeah, but it also may be lower if sometime in the past you were closer to the destination than you are now, and something happened which increased your distance. The highlighted word here, or the keyword here, is ever. Well, ever as historical minimum, my historical minimum starts and ends with that active computation when I need to start coordinating with you. Because if I coordinate with you, I know that I get up-to-date information. When I don't need to coordinate with you, I'm trying to make my choices based on cached information. And that's where the feasible distance comes in. It's the distance that I've experienced in the past, the smallest one, not necessarily the current that I have. It has some funny properties if taken this way. Feasible distance, first of all, is just one per destination. It's not computed and stored per neighbor. Second, it's a local variable. It's a local value. We never send it to anybody out. You never share that information because that one is used for your local path choices. Others have their own. And third, in passive state, the feasible distance can only go down. It can never rise because it's the historical minimum. A minimum doesn't rise. A minimum can only go down. The moment you need to increase the feasible distance, because you cannot choose any next hop, that's why you fire up the active state and need to go with this all diffusing computations. Let me show you something. So we have this topology running in my backstage. I will be working from router R1, and I will be focusing just on the link between R1 and R2. Currently, its cost is 5, and I'm manipulating one of the two configurable EIGRP metric components, the delay, to use this. So currently on that link, the delay is configured to be 5. Let me see what happens if I bump it a little. Coming back to my Linux. So this is how my interface E01 is currently configured. And yeah, that would be my interface. I just need to stop the session mode here. Pardon me. Okay, here we go. Apologies. So this is the delay configured there. And just so that we have up-to-date information from the EIGRP topology table, this is how it currently looks like. Notice that for now, the feasible distance is set to a ghastly value, which is really 11 times 65,536. You know, we did these multiplications there. And momentarily, it looks like it's truly the same as the path through the guide that provides the smallest distance to the complete distance to the destination. Let's see what happens if I go to interface E01 and increase the delay a little, say to 7 from 5, just to see what happens. If you try this at home, you can try this at home. Give it about 10 seconds for EIGRP to take notice and do the computation. And now I'm going to ask the EIGRP topology again. And now notice something that the textbooks are conveniently silent about. The feasible distance didn't change, but the true distance, the computed distance, this one did. Is this a bug? No, this is a feature. Because the feasible distance is the minimum, not necessarily the current distance. Why do we need it? I'll be talking about the feasibility condition in a second. That's where we need it. But for now, just please trust me that this is by design. And if you see such a situation in your network that the feasible distance seems to be different from your best distances that you see over individual neighbors, that's okay. That just meant that at some point in the past you were closer, now you're farther, but that's okay. That's normal. It's fine. Coming back to the slide deck. Just keep this information for a while and just set it aside for a while. And let me ask you about this. Feasible successors. They are immediate replacements for next hops. So if the next hop dies, the feasible successor kicks in. Who thinks this is true? A couple of people do. Who think this is false? Nino does. Okay. Let's see where the truth is. Again, just to be sure that we understand the keywords here, again, a reminder. What's this feasibility condition I've mentioned? Well, again, there is a couple of textbook definitions that says it's a rule by which we make loop-free decisions about who is guaranteed to provide the loop-free path, and the others, I'm not sure. So I won't be using them blindly, and if I need to use them, I will ask first. That's the whole goal of the feasibility condition. Feasibility condition says formally that if my neighbor's reported distance is smaller than my feasible distance, then he provides a loop-free path. But can you remember this? I had to sneak in and look at. I remember it when translated into the human speak using the definition of the feasible distance before. I said the closest we have ever been. So with this, feasibility condition says, if you as my neighbor are closer to the destination that I have ever been, then you provide me with a loop-free path because you have never been using me, since otherwise your cost would be derived from mine. This is how the loop freedom in EIGRP truly works. If you are closer than I have ever been, I can be certain you haven't been using me in the past, you are not using me now, I can go through you. That's what the feasibility condition does. And now, routers that satisfy this feasibility condition are called feasible successors. Those are the neighbors that just pass this condition and nothing more. And on top of it, if you have neighbors that satisfy not just the feasibility condition, but also the fact that they are providing the least distance, they are successors. So just a short thing, a short wrap up. A successor is loop-free and provides the shortest path. A feasible successor is loop-free but does not provide the shortest path. It's longer, but still loop-free. That is important. So how do we use the successors? Well, the successors, as I've just said, they provide the shortest paths. So naturally, they are the next hops. Feasible successors, well, they don't provide shortest paths, but still ones that are guaranteed to be loop-free. We can use them if we do this unequal cost multipath with the variance command using worse paths, but still those that are guaranteed to be loop-free. And we might use them if my current successor dies, but not always. And what's the rule here? What's the rule here? Coming back again to the same topology with the same link costs as always. If I look at the distances from R1 to that IPv6 network on the right, on R5, the top path through R2, the total cost is 11, and it's the shortest one. The path through R3, the total cost is 17, 8, 16, and 17. But it's loop-free because R3 guy, his own reported distance currently is 9, which is less than the best I've seen so far, 11. So this is the feasibility condition. And finally, I have the path through R4. The path through R4, notice that it's shorter than the path through R3 for 16, but R4 does not meet the feasibility condition. R2 is the successor. R3 is the feasible successor. R4 is nothing, but still provides a seemingly better path than the feasible successor. Now, if the link between R1 and R2 died, the textbook would say, oh, you have a feasible successor, go and use it. But if you did, you would stay on a loop-free path, but not the shortest one that's available or might be available. That's the better way to put it, might be available. So what in reality happens here is, actually, let's do that debug that I promised you. And we're closing, by the way, to the closing of the session. So we're all good, on time. So I'm going to do debug EIGRP finite state machine. And I'm going to do what I promised you. I'm going to kill the link between R1 and R2. Remember, we think also based on this output that router 3 should be the feasible successor. We should kick in and just use it and not go active and start sending queries and that everything. Nonetheless, let me go up here, scroll a little. I know these numbers are terrible to read. Notice this part here. What EIGRP did here is first update the distance because we needed to process the event. Then went neighbor by neighbor that advertised the network to us and tried to find the one that provides the shortest path. The shortest path is provided by router 4, FE80::4. But you remember from the diagram where I just had nicer numbers, that one was not a feasible successor. So I don't want to miss the opportunity to use the shorter path. Hence, I will need to go active and I will need to start sending queries. And whilst it's not visible a little here, I'm going to send queries. I didn't do the packet capture, but you see I'm receiving replies, meaning I was sending out queries. I had to go active. And suddenly, in this state, my next hop now becomes 4, and 3 remains a feasible successor as it was before. So the whole logic that EIGRP does, to come to the closing slide, since we're running out of time, the goal EIGRP has is to always do loop-free decisions. So the whole logic is whenever something happens in the network, and this is really simple. First, update the distances in your topology table so that you know that you're working with the up-to-date numbers. Then, find out the neighbor who provides the least distance to the destination. Easy. And only then verify if that neighbor is a feasible successor. If it is, yay. If not, go active and ask. Maybe it provides the least path, in which case you can raise the feasible distance, start from scratch, and start using it. Or maybe you find somebody else. That's how the EIGRP does. Don't be surprised. And again, this is by design. This is how it's intended to work. Not a bug, it's a feature. My completely last question, and there is nothing else, just the thank you slide. Does EIGRP use the MTU parameter as a part of the metric computation, or can it be done that EIGRP takes MTU into account? You know, because we always have to configure bandwidth, delay, reliability load on MTU. There's a nice help. Big dogs really like me. Bandwidth, delay, reliability load, MTU. Can EIGRP be ever made to use the MTU? No. If you go into the trouble of looking up those formulas, the formula doesn't have MTU anywhere. EIGRP never did it. Never, not in the present, not in the past. It was envisioned, but never implemented. As simple as that. Don't search for any deep meaning. With this, hopefully, now at least 30 people know more about the EIGRP.